In this video, I'm going to be using sinusoidal equations to calculate x, v, and acceleration in simple harmonic motion. Please take a moment to read the success criteria I plan to cover in this video. In our data booklets, we have the following equations. Now, in this case, displacement is x naught, which would be the amplitude. I'll mark that on here. Sine omega t. Now omega, if you remember, the period will go from here to here. That's the period. And omega, the equation's in the data booklet, 2 pi over the period. It's the angular frequency. Now, this is the phase shift. In this case, since my graph starts at 0, 0, the phase shift is actually 0. That is our normal sine curve. I like to think of this oscillation here as broken up into 4 parts. 1, 2, 3, 4. And we know that one full oscillation is 2 pi. And what that means is each one of these quarters is actually going to therefore be pi by 2. So this would be pi, 2 pi. So what this phase difference is if I didn't start at 0, 0 and I didn't have my traditional sine curve and my graph was actually shifted left and right, that's where this value comes in. If, for example, I had that phi being pi by 2, it would actually look like this. And if you're saying, oh, that's a cosine curve, you're correct. So, if I have my equation, x equals x naught sine omega t plus pi over 2, I could have written the exact same equation without the phi and replaced sine with cosine. Sometimes that's just easier to do. So this graph would look like the cosine curve. Likewise, if my graph looked like this, let's say I started at the negative side, I could then put, instead of just sine here and a phase difference, I could just write it as being negative cosine omega t. The other equation we have here is that we've got the velocity is this omega x naught. Again, on my graph, this would be then the amplitude, the value in front of the cosine. In our case here, it's related to our displacement time graph, but it's not exactly the same. And you can see I start here at time equals 0 with a maximum value, which is why they wrote cosine. But again, we don't always start our time equals 0 with a maximum speed at time is 0. So we may end up having a phase shift. Don't let that panic you. It's there just so that we can give variations of these graphs. We don't have to start at these exact points. Now, we also have this equation right here. Let's take a look at the difference between this one and the one I had before. If I have a velocity and I know it was cosine, I know how long it's been since time equals 0, I can use this equation. But if I don't know what time I have, but I know how far away I am, I'm going to use this one. So, for example, if I only know that I'm here, at this point, because it's a specific distance away from my origin, remember, at the top, the amplitude is x naught, and my point here, if I want to know the speed at this point, I'm going to use x equaling this value. You might say, why is there a plus or minus? Well, in this case, I'm on the positive side, so I'm going to be using a velocity that is negative. You can see that I'm about to go back towards the equilibrium. I'm moving in the negative direction. If I was down here at that same displacement, same distance here, now I'm still going in the negative direction. I'll be going just as fast. Remember, slow down, stop. Now I've turned direction. I could be going the same speed, but now I'm going in the positive direction, so this would be a positive velocity. So negative, negative, and positive. There's one more graph I want to point out, and that's an acceleration versus displacement graph. Remember that for simple harmonic motion, our acceleration is directly proportional to the displacement, but they're in the opposite direction. That's what this negative sign is for, the opposite direction. This is a condition of simple harmonic motion, and now if I want to write it as an equation, I would actually write A equals negative omega squared x. On the graph of A versus, nope, this should be an x, I will end up having a graph which is a straight line. And the gradient will equal omega squared. You can put the negative sign there. Notice that when my object moves in a positive x direction, it becomes a negative acceleration value. When it's in the center, when I have a constant velocity, my acceleration is 0. As it moves back to the negative x direction, I end up having a positive acceleration. If I'm over here in a positive acceleration, it means the acceleration is towards the center. And that's the other condition. When we talk about opposite direction, we can also say that the acceleration always points towards the center, or the equilibrium. Okay, so let's go through a few examples. I have a body in simple harmonic motion. Doesn't matter, it could be a pendulum, a mass spring system, anything. But I do know the amplitude is 0.6 meters, so I'm going to write that down. And its period is 2 pi. What is the speed when the displacement is 0.3 meters? So this is one of those cases where I know where it is. I need to use this equation. Now, you might say, what about the plus or minus? It does ask for speed, so I'm only interested in the magnitude, and I don't need a plus or minus. So let's substitute in some values. Omega is 2 pi over the period, which in this case says 2 pi, root 0.6 squared minus 0.3 squared. Don't get tempted just to say this root sign cancels out and all of this is 0.3, because order of operations means I have to do the squaring first, then subtract, and then the root sign. If I pick up my calculator, I get 0.52 meters per second. So what is the phase difference between the displacement and the acceleration of a particle moving with simple harmonic motion? Well, let me just do one example of displacement time graph, and let's just do the simple sine curve. Now we know for acceleration time graph, acceleration is directly proportional to the displacement but opposite in direction. So if I go to a positive x here, I need to be going to a negative acceleration here. And there'll be maximums at the same point, 0 at the same point, and I can do my graph. So in order to go from my x sine curve to my acceleration sine curve, you can see I need to go this far, and I need to push this one over 1/2 of my oscillation. Well, one oscillation is 2 pi, and I have to go through half of that, so that means they are going to be pi out of phase. My answer is B. Okay, example 3. Here is our displacement time graph again. It tells us the mass, and it's asked us for the period of the motion. Now you might be tempted to use this value about right here, but you cannot be sure that it's actually the peak. So to be honest, I wouldn't use that number. I would either go from here to one complete one, or I can see this part really easily on both the troughs. I would take these 2 points to measure my period. And in this case, this was 0.15, this one 0.45. Remember, IB will expect you to read your graph to the nearest half square, and that means that my period is going to be 0.3 seconds. Part B, calculate the maximum speed of the mass. Now there's a few ways you can do this. I would say, because reading these times, it doesn't cross very precisely on my graph, that I don't want to use the time and the fact that it's a cosine graph. Again, we don't know if it's perfectly up here. I think this value, and it is speed, I can forget about the plus minus. I think this equation is the better way to go. Now, our x naught, our amplitude here, is 1.8. And at maximum speed, we know that occurs at the equilibrium where x is 0. Let me put in my values. 2 pi over the period for omega, 1.8 squared minus 0. And if I pick up my calculator, I get 38. Now this distance is in centimeters, so that will be centimeters. My time is in seconds. So centimeters per second. Part C, mark on the graph the point of maximum acceleration. So since acceleration is proportional to negative x, that means the acceleration max is at x max. So that means I can choose this point here, or I could use either of these troughs. Again, we don't know if that really is a peak. I would not use that one. And let's use a graph that might have been new to you. We've got a mass here. It's hanging on our spring. We're going to say B is at equilibrium. A was B when I pull it up. C is if I pull it down. Now, in this case, we know it must be an A versus X graph. If I mark these pieces on here, my equilibrium is where my X is 0. And over here, where my X is positive, I'm going to say up, and that's going to be positive. And this down, let's say this is negative. So that means when my X is positive, A will be here, and C would be here. Now we have a spring constant, and the distance between B and C is 0.12. B and C, this will be the amplitude. Now we're looking for acceleration, but in order for me to use acceleration, I'll need to have omega. And in order to get omega, I'm going to need the period. So for a mass spring system, we know we have this equation, the mass over the spring constant. If I put my values in, I'm going to put my mass in kilograms because this is in newtons per meter. And remember, hidden inside a newton is a kilogram. So 2 newtons per kilogram. Picking up my handy dandy calculator, I get the value of 1.26. So I'm going to go back over here. A equals negative omega naught. Omega is 2 pi over the period squared x. And since I'm looking for maximum, x is going to be at x naught. And I really do suggest you write down things like this. Because if for some reason a mark scheme says the mark is awarded for use of, or recognizing where the maximum acceleration will be, then just doing this can sometimes get you a mark. Let me put in some values. 2 pi over 1.26 squared. My x maximum is 0.12. Picking up my calculator, I get the value of 2.98, but looking how these values are all two significant figures, I'm going to round that to 3.0 meters per second squared. So please read the success criteria one more time. I'm hoping that after this video, you can say yes to the following bullet points.